All right, we are now recording. Please proceed.
All righty, I'm Jonathan L.
I'm Wyatt Leisure.
Eric Carrasco.
I'm Dylan Mullen.
And we were responsible for the Enerpac battery torque wrench gearbox. We were approached by one of MSU's industry partners, Enerpac, to create a gearbox for their 3,000 foot-pound battery torque wrench, and to ideally make it smaller, lighter, and easier to handle, such that it can be used for mobile applications like climbing wind turbines. To do this, we started out by generating the problem statement, what we need to do, our objectives, constraints, what are our goals, and what requirements do we need to meet. We looked around at some previous iterations of similar products like torque wrenches, planetary gear sets, and similar applications. We generated a couple of ideas for our final design each, and we compared them by a design matrix in the trade-off study to figure out which of the designs would be going into our final design.
So our problem statement was the gearbox in Enerpac's new battery torque wrench series 3,000 pound-foot torque wrench is excessively long and heavy, resulting in increased user fatigue during operation. Enerpac requires a redesigned gearbox that is shorter and lighter than the current model while maintaining the current torque output.
Beginning with what we were hoping to achieve and what we were absolutely required to achieve, we wanted the gearbox to be lighter than the current model, be shorter, and following from those things, to move the center of mass closer to the handle for easier handling. While doing this, we also needed to maintain a final output torque of 3,000 foot-pounds, and attached to both the Metabo motor and the square drive adapter, and to be able to withstand a total of 10,000 cycles at the highest stress.
Moving on to our background research, we have a few patents and articles that pertain to our design that helped us out during the design process. This first one here is just a simple torque wrench patented back in 1969 with the use of rotary inputs with planetary gear sets that increase the torque output. Just a great starting point so that we all are on the same page and know exactly what a torque wrench is.
Following from that, we looked into some other profiles for planetary gears. One of the first looked at was an AA planetary gear set, which uses the planet gears meshing with each other to reduce stresses by distributing the load across more engaged teeth. We didn't end up using this particular design today because it's already patented, but also it was still incredibly helpful for, especially in later stages where stresses were high, to know that we could spread out the stress over a wider or over a greater number of engaged teeth to increase total strength. It's also similar but distinct to a later design in the double pinion.
And moving into this project, we knew that if we were going to be designing our own gears, we're probably going to need a way to manufacture our own gears. And once we read this article, the number one solution to making those gears were probably going to be metal 3D printing. Metal 3D printing has like the biggest upside of just high accuracy in manufacturing. What you put in is what you're going to be getting out. Though it does have a drawback of typically a low quality surface finish, though with additional machining such as like polishing or sanding, that can be remedied. Another thing to think about is actually the material that we're going to be using in metal 3D printing. The material that we went with is a titanium, vanadium, aluminum alloy that's called Ti6Al4 or just Ti64. We picked it mostly because of its high strength to weight ratio, high melting point, and then corrosion resistance is just another bonus, but typically not too much to worry about when it comes to gearboxes. But Ti64 is already common in metal 3D printing, so it just seemed like the way to go for our prototype.
So this article discussed cutting out sections of the planet gears for the planetary gearbox of a wind turbine. They were able to achieve 11% reduction in mass and only a 0.6 increase in maximum von-Mises stress. Similar methods will help us with reducing our weight and keeping it under the optimal weight?
At this point, with the bulk of our research done, we moved on to some design formulations, beginning with the duplicate carrier-driven gear train. Now, Enerpac generously provided us with a sample gearbox for a similar torque wrench, and the design used was very similar to this. This is pretty much your stock and standard planetary gear set. The rotation of the sun drives the rotation of the planets about the sun. This orbit is what is called the carrier, which gives us the reduction for the next stage. This also means that the reduction is given by the ratio between the diameter of the sun ring, or the sun gear, and the ring gear, which gives us a large reduction while keeping the torque along a central axis and not displacing it. With a conservative ratio of 1 to 6 per stage, specifications can be met within 5 stages. Additionally, by having repeating gear sets, i.e. the same gears repeated multiple times, we can cut down on costs for manufacture by hopping them all at once, or perhaps if CNC machining comes in, fewer program rings are required, especially helpful for prototyping. It also allows for the ring gear to be fixed within the case, meaning no bearings are required between the edge of the case and the ring gear. It can be integrated directly into the case.
So the next design we looked into was a double pinion planetary gear. This type of gear train is basically a conventional planetary gear set, except you're adding a additional planetary gear in series to your standard planetary gear set. And what that does is basically amplifies the original ratio of a standard planetary gear set to get a much higher output ratio than a traditional planetary gear set. It's effectively turning 2 stages of standard planetary gears into a single stage. There is going to be less room for additional planets. So as you can see in the picture, if you try to add a 4th planet train, most likely you would not have space for it given our maximum outer diameter constraint on the gearbox. But it would help significantly with cutting down weight and length of the gearbox.
So this is like coil drive. You have an eccentric cam, which drives the cycloidal disc, which causes the carrier to rotate. It reverses the direction, but it handles more stress than a gear, and it's easier to machine than gears. It has friction which leads to wear, and it will create a wobble action in the gearbox, but both those can be counteracted. The wobble can be counteracted by having 2 discs per stage that are offset by 180 degrees, and lubricant can be used to reduce the friction.
Another design is the split ring compound planetary gear. This is again essentially combining 2 stages of your standard planetary gear, except this design actually creates a much higher output than a standard traditional planetary gear. Basically, what it does is you have the input of a sun gear, which drives planets to a fixed ring. Those planets are connected to the secondary planets on the outside, which then go to a output of the secondary ring gear. There is a second sun gear in there, which is just an idler gear. It's just helping get the second planets to stay in position and not to bend inwards or misalign themselves. But this does create an incredibly high gear ratio, but there could be problems due to not the gear teeth not being able to keep up with such high torques. But the additionally, dust and can enter through the gaps between fixed and moving ring gears, and you will also need a bearing for the moving ring gear.
It's also worth noting that the original design consideration, we were given a choice between a 6,000 foot-pound and a 3,000 foot-pound battery torque wrench. And so we briefly investigated being able to do both. One of the methods we came up with for that was the direct drive clutch. Essentially, this would work with a carrier-driven design by fixing the rotation of the carrier to the sun and allowing the ring to rotate freely. It could remove the speed reduction for that train, allowing it to basically gear up and gear down within the planetary set, outputting vastly different torques. However, since we eventually decided on sticking to 3,000 foot-pound, and also because this is extremely difficult to implement, because it requires the carrier to be pinned to the sun, difficult to implement in any mechanical way without disrupting previous gear sets, and that it will require the ring to be able to rotate freely, undoing some of the advantage of the carrier-driven design in the first place. This was eventually scrapped.
A helical gear train, for this design, it works just like your standard planetary gear set, except instead of spur gears, it uses helical gears. The biggest upside is that the increased contact stresses contact area between the gears will reduce the bending stresses on all the gears, making the life of the gears last longer. The bigger downside, or some downsides notably, are the thrust forces that come with helical gears. The geometry will force the gears to sort of like, well, thrust forces. And that could either be remedied by having a specific bearing that counteracts it, or having alternating stages of flipped angled gears. Though probably the bigger downside that matters the most is just the manufacturing cost of helical gears. They can cost upwards of like 40% more than your average spur gear, and when you're working with a company, sometimes that can just not be worth it, especially when it hasn't been fully implemented yet. Though it could, while we are not using the helical gears, it could still be useful for a future iteration. Yeah.
So each design was scored 0 through 10 for each criterion, with 0 being the worst, 0, 5. 0 being the worst, 5 being the best. We assigned weights to each category. Each categories being weight, cost, number of stages, length, and ease of implementing. Ease of implementing being how easy it is to design and manufacture. Weight and length got the highest scoring, or the highest weights, because they were most closely related to our objectives. And then we each individually completed the decision matrix and then averaged our scores to create a team decision matrix, with the winning design getting the highest overall score. So here's our decision matrix. As you see, the highlighted values are the winning ones for each category. The split ring won for weight because it will require fewer stages. Cycloidal had the highest score for cost because it's the cheapest to manufacture. It also won for number of stages and length because it can handle higher stresses. Each stage can be thick. Carrier driven won for ease of implementing, since it has fewer gear profiles that we need to design. And finally, the total winner was split ring compound planetary gear, because it had the highest total score.
So here we have our prototyping pad files. On the left, you can see it's the split ring compound planetary gear. That is acting as our first stage and our main reduction of the gearbox. It follows up by having 3 stages of traditional planetary gears, with the third stage being slightly longer in length due to the higher forces coming onto that gear. It has a 1 to 6,800 gear ratio. Looking into stage efficiencies, with about an 85 to a 90% stage efficiency, it would come out to about 1 to 5,900, which outputs a torque of 3,500 foot-pounds for an input torque of 0.6 to 0.7 foot-pounds. Here are the gear ratios that we use. We have the diametral pitch, the ring sun planet tooth relation, the planet sun center distance, and stage ratio. All of those are for your traditional planetary gear sets. On the other side, you have the split ring equations for your tooth relation, your common planet center distance, and your Wolfram ratio. Below that, I put down our final gear ratios per stage. So first stage 1 to 252, and then all three planetary gearbox stages are 1 to 3. Using this design, we cut down the length of the total gearbox to 7 inches, which is a 36% reduction in length. That is excluding the square drive end of the gearbox and leaving about a 1/4 inch for the carriers between stages. It does have a 1/2 inch bigger maximum overall diameter of the gearbox in comparison to the original Enerpack design, but that can be modified to optimize that a little bit just by lengthening the gearbox or adjusting the ratios.
And examining this design for final stresses, we took a look at the final sun gear, as it is both the gear with the smallest gear with the highest applied torque. This torque was calculated into the tangential force from its diameter and the number of teeth engaged in handling that force. And then using the gear stress equation was taken with the diametral pitch, the final length of the tooth, and a Lewis factor of 0.2. Which gave us a final stress of 60.31 KSI, rather high, but with the stresses were reduced substantially by lengthening the final tooth and engaging it with more sun gears. This was then compared to the endurance strength and the fatigue strength at 10,000 cycles. The endurance strength was calculated with a surface factor of 0.57. This is because both hobbing, the traditional method for making production gears, and metal 3D printing tend to have a poor surface finish. So this could, while this is the limiting factor, it could very easily be heightened by giving it another run through and smoothing out that surface a little bit. The size factor for a small diameter gear is just 1. KC, the loading factor, and bending is also 1. The temperature factor, KD, the lubricant in this case is both as a lubricant and as a way to absorb heat. So this does not need to be considered as, thanks to the case being well lubricated, does not get that hot. The reliability factor taken for 99%, 0.868, and the SE prime, the adjusted ultimate strength of 85 KSI for the TI64 material, gives us an endurance strength of 42.4 KSI. I regret to report this thing will not last forever. However, because the final stage moves at less than 1 rotation per minute, it only needs to last 10,000 cycles. And adjusting that formula for the fatigue strength at 10,000 cycles, it has a fatigue strength of 152 KSI, giving us a final factor of safety of 1.48.
Here we just have the tentative schedule for the spring term. As we can, or one big note, I should say, is week 2 is a stress analysis and tolerancing. Now, these equations have already been worked on. This is mostly just to be a checkup stage to make sure that everything's all up to snuff as we previously determined. And of course, there's going to be a lot more cooperation with Enerpac to figure out how exactly the parts are being made with like the type of metal 3D printing. Another question that could be solved is the budgeting, which of course, once we figure out the type of metal 3D printing and once the design is finalized, because it is not impossible for any for the changes to be made between now and say week 4 of next semester. But once those are completely set in stone, the budgeting should be figured out. That should be all.
I would like to open the floor to questions.
All right. Questions, anyone? Let them have it.
That's a bad sign.
Do you have to do any sort of heat treating after the metal 3D printing with that material?
Not for titanium, no.
Okay.
Obviously for a final production, which would probably be some kind of carbon steel, that would be a different matter, but.
So you guys gonna 3D print it? How are you gonna polish it and still maintain the geometry and accuracy?
Well, the calculations were done with a poor surface finish in mind, because we want to be conservative, especially with very high stresses. But a surface finish could be used to reduce those stresses, but it isn't a necessary step, especially for a prototype that probably won't be going for 10,000 cycles. But a lot of things could be implemented to reduce final stresses, like implementing helical gears or bringing out that surface finish, or even just widening the final stage.
Is there a reason you didn't use 2 sets of compound planetary gears instead of pairing it with traditional planetary gears?
Yeah, so the compound planetary gear set, one, it's not a very widely used gear set in industry. So it doesn't have too much literature behind it. But what I've seen is the stage efficiencies can be on the lower end compared to traditional standard planetary gear sets. So if you put both of those back to back, it would create a higher ratio, yes, but it would create a significantly lower effective ratio.
I have a couple questions. Two of them are regarding your use of the Lewis formula. How many teeth are in contact and where did you come up with that number?
The teeth in contact we took from the minimum of engaged sun gears, which would be 3 for the stage. And the Lewis equation was used because we don't currently know the final tooth profile. So a more refined equation like an AGMA equation would be a lot of guesswork. So taking a equation that can take out some of that guesswork, simplifies things a lot.
That was my second question. So thank you for answering that question. Other questions?
I have, how do you define the cycle in here? What is one cycle?
That is 1 turn of the sun gear.
Stage
Or
sun
the-
gear.
And 10,000 cycles, how long does it take to get torque wrench to achieve?
That is not a question I've done the math for, but considering it's a 1 in 3,500 roughly speed reduction, the final sun gear moves less than a rotation per minute. It's a substantial life. Also, the 10,000 cycle was given to us directly from Enerpac. That's a ARC requirement.
So you didn't look at it in detail then. The other thing is, can you show me the gear set that you have and explain how it is working? The last final diagram that you have. Here.
So basically, you would get your input from your Metabo motor onto the sun gear, which drives the planet gears. These planet gears on the split ring are connected to the second split ring planet gears, which then drives this output ring. That output ring will act as the carrier for the next stage, which then drives the second stage planetary gear set, driving the sun gear, and then that sun gear drives planet gears. The rest of the ring gears are fixed, so they are part of the case, the gearbox case. So each stage of your planetary gear is getting driven by the previous stage's plans.
If you were to get something failing in here, what would fail?
Well, the reason we evaluated the final sun gear is because it has the greatest applied torque being the, or the greatest applied torque relative to its size being the final, gear in the train having the most speed reduction. So that's where the tangential forces will be the greatest. If the carriers are under a great deal of stress, it is why, we are confident in allowing them to be so thin and allowing a quarter inch for between stages. But long story short, we're mostly worried about the final sun gear failing.
Is this the only thing that you designed, or do you have to worry about shafts? You have to worry about anything else that?
Well, we do need to worry about it connecting both to the Metago motor and the square drive output, but that's just sticking an adapter at the end of this carrier and an adapter and a shaft at the beginning of the first stage sun gear.
So wouldn't you worry about those members failing?
They can be made substantially larger than the sun gear.
I think you should really consider the whole package and look at what is failing. You can get the best gear, but if you have something else that's going to shaft is going to fail or the key is going to fail, you have to worry about those products. Yeah. But this is fitting exactly what they have. The limit of length was, you said something 6 inches, something like that.
7 inches long, 36% reduction.
So this fits into that the range that you showed at the beginning, right?
Yep.
So a quick follow-up on that, you said the overall goal is to reduce weight or volume?
Reduce weight, reduce length, and an additional thing that we try to do is shift the center of gravity back towards the handle of the torque wrench a little bit, just so it's easier to handle. And it, with the split ring being the first stage, that's going to be the heavier part of the gearbox, so the center of gravity should be shifted back towards that first stage.
So you've done the volume calculations. Have you looked at the mass at all of these? Because if they make it smaller, did you have to increase the density and make it?
If I'm remembering correctly, it's just about the same amount of mass. It might be slightly.
Okay.
This is also where the mass production profile Harrison mentioned in our background research would be tremendously helpful, especially for stages that are under lower stresses.
I have one more, with the ring gear moving, you've got the one ring gear moving. What kind of issues might that cause with the construction of the case?
Well, first off, you need obviously a bearing on the outside of that ring gear between the case and the ring gear, just so it has that be able to make that motion concentric. But it could create issues when it comes to manufacturing the case. So if we are making this case all in one, and we have to push a bearing in there, first off, it's going to be a slightly wider diameter to the just this gearbox is already a half inch over in diameter compared to the original design. But adding a bearing to that moving ring gear would make it wider in diameter. But if you try, if basically it's just going to add a little bit of complexity onto the manufacturing side of the gearbox.
All right, are there any last questions? Otherwise, we're just about out of time. All right, thank you, guys. What's that?
Yeah, we maybe stay about.
Hey, nice job, guys. Yeah, you bet. My pleasure. I got up early, especially to come.
It's not because they have.
Yes.
Okay.
It's really not, you guys how many sort out for you, why does it exist? The thing with the biggest power.
I'm ready when you are.
It's gonna take 30 seconds.
I appreciate it.
Thank you.
Alright, hello everybody. We are the Milwaukee Tool Cutoff Saw team. My name is Andre Daniels.
I'm Toby Engel.
Ryan Lemay.
Fine, legal.
And Tober Nico.
All right.
Ooh, technology failure.
Switch the USB.
Oh, there, oh, there.
I don't.
Sorry. Walking across all of us. Okay, so this is Gilbert. Gilbert is a general contractor who works with concrete on a daily basis. Gilbert values quality tools, and that's why he buys from Milwaukee Tool. This makes Gilbert a very valuable customer to Milwaukee Tool. So he buys a Milwaukee Tool concrete cutoff saw. The problem occurs when he starts using it. When he starts using it, it starts stopping early, it starts overheating. And then throughout the day, he has to stop several times to replace the battery. Now, Gilbert is disappointed. Ever since he's got the tool, the time to do the job has increased. And this has made his company less profit.
This isn't just a hypothetical situation. This is something that a lot of users have been reporting and facing. 75 out of the 109 reviews on the Milwaukee Tool website mentioned issues with the battery life, 39 specifically with overheating.
Yeah, so we know this overheating causes a few problems. First is performance loss. It reduces the lifespan, durability. It causes thermal shutdown, which decreases the efficiency for our users. Knowing this problem exists, Milwaukee Tool approached us and asked us to integrate some type of water cooling into their saw, investigate if that would be efficient and how that would work. The only constraint we really have was to use that existing water supply, which is already used to reduce dusting when cutting concrete. Hopefully, this should improve the tool performance, the durability, and most importantly, user satisfaction.
All right, now we've defined the problem a little bit. Let's understand it better. So what do we know and what we don't know? What we know is that the saw overheats, and we know it doesn't run as long as desired. What we don't know is how long does it currently run? How hot does it currently get? And specifically, where are those hot points? So this has led us to controlled experimental testing.
So how do we want to test this? Well, we know that when the saw is in use, it gets really hot, which is where those thermal issues come into play. So we wanted to make a repeatable process to get and collect that data to be able to understand how hot the saw is actually getting, while also running that through simulations to understand how we can better fix it with water cooling. So to start, we decided that we wanted to do a test fixture to make those repeatable processes.
The test fixture needs to accomplish two things. It needs to fix the saw's location in space and apply the controlled load. The first of these designs was based on a simple bike brake. The second design was based on a worm gear meshing with a spur gear. The third design was based on a friction disc and a rope. The fourth design was based on back charging a different motor. The fifth design was based on a scissor jack mechanism. And the sixth design was a perpendicular power screw. Now we took all six of these designs and put them into an engineering matrix. We had 6 different categories and we had assigned weights that were relevant to this project. All of us voted on each of those categories for each saw, 1 through 5, and the average was taken for each of those categories. Those scores were then weighted, and the total was tallied up below. And idea 6, the simple power screw design, came out on top.
So as we started to develop this idea more, we ran into a problem: the rate of load application. With the current design, the only adjustability that we have is the movement in the brake pad. This is not really what we want, because the point of the test fixture is to match what forces we will see in real application. So we have a very steep force application curve. To address this, we included springs into our mechanism. So this is the mechanism that we came up with, and you can see our prototype here. Using the threads per inch of the screw and the spring constant, we were able to make a mathematical relationship between horizontal movement in the screw and normal force applied to the blade. So this is going to go through a little bit the creation of our test fixture. This is the very initial model that we came up with. There's two big takeaways that I want you to notice. One is we have somewhere to apply a brake fixture, or braking mechanism, and then another location to fix the saw too. From our initial design to our final design, there are two big errors that we corrected. One was adjustability. With our test fixture, initially it was all welded. All of our joints were welded. And two, all of our parts were not based in real applications. To address this, moving to our final design, we included bolt and slot connections throughout the test fixture to allow adjustability in future testing. And then we also standardized materials. This is a very common thing in industry, preventing us from buying several individual parts and allowing us to buy in bulk.
Right. Now that we have that fixture design out of the way, this is the final fixture that was fabricated. So as you can see, this red part is the piece that is attached to the table. This fixes the saw in space. This yellow piece reaches up and it mounts to the already existing holes that are in the saw, the part that's used for the handle. The green part holds the braking mechanism, and this braking mechanism is made up of a few different parts. This first part here is the power screw. This power screw threads into the nut. This nut is welded directly to this plate, so as the power screw turns, it pushes this braking assembly closer to the blade's face. Now, once the brake makes contact with the blade's face, the springs begin to compress and force is applied. These are the pieces of the fixture. So each of the material that we got was a stock piece of steel. That piece was cut in using a bandsaw to get the individual pieces. The holes were cut on a steel mill, and the entire thing was assembled and welded together. Initially, we just tack welded everything to check the fit with the saw, and once that was fit good, then we finished out the welds, and this is the final fixture.
Then moved on to the cooling design phase. The first thing that we wanted to do was look at the actual electronics in the saw. As you can see, there are about 6 different boards in the saw. The two that we focused the most on were the motor or power board and the control board. This is because the motor board's responsibility is to switch the battery current from the battery to the motor, which requires a lot of power and has these 6 components here, the MOSFETs, that are kind of known to be those thermal hotspots. So that's where we wanted to look. And then also the control board, which manages the firmware and a lot of those motor commands, that has a microcontroller that also is a potential source for heat. These boards also had potting on them. The control board had a thick black urethane for dust and water protection, and then the others had a yellow adhesive for just mechanical and electrical insulation that we also had to look at for kind of the thermal conductivities. The first testing that we did was just a simple no-load test. This was running the saw with the blade removed and a stationary thermal camera to kind of quantitatively identify those hot spots. The microcontroller on the control board actually got the hottest out of the components. We also noticed that the MOSFET showed heating. The battery actually stayed near an ambient temperature, which we thought was really interesting, seeing those user reviews. This kind of allowed us to inform our placement for our concept design of the water cooling.
Yeah, so now knowing where where our thing is heating up, we wanted to find some techniques to actually cool it down. So first we looked into some heat pipes and vapor chambers to show us how we can take advantage of the water cycle and those small contact zones on the chips. Next, we looked into some cold plates, showing us how something simple could still be effective. We also looked into some plate fin heat exchanger, showing us how we can increase surface area to increase that heat transfer. And then we looked into YouTube and immersion coil heat exchangers. So showing us how we can manipulate the inside of that water stream to use that to our advantage to get rid of some heat in our system. We also looked into some actual solutions used, such as CPU water blocks, immersion cooling, and microchannel heat sinks. This was also to give us some more ideas on what possibly we can implement into our design. Finally, we decided that something like a cold plate would be most applicable for us due to its simplicity yet effective transfer of heat.
Now, after kind of discussing what ideas we could do, we wanted to get some rough sketches on what this idea would look like. So our first concept and idea, which was nicknamed the sandwich, utilizes this cold plate idea and both sides of the cold plate for the most amount of surface area to have heat exchange with. The bottom side of the cold plate would be mounted to the top of the motor board where those MOSFETs are. And then the top of the cold plate would have the PCBA board mounted right on top, face down on it. Like I said, this way we'd be able to utilize both surface areas in the small work area that we have and hopefully have the most amount of heat transfer. The second idea was very similar to this. However, we would keep the components where they currently are mounted within the saw and just route piping and cold plates to each separate location. The third idea was a water chamber. This was kind of our alternative solution in case these first two didn't work. And you kind of utilize the idea of if we can put water almost directly over these electrical components, like how like a CPU water cooler works, see if that would also be a useful tactic. We wanted to consult the rest of the group to see which idea we posed as the best. So we had our own weighted criteria that we felt matched what values and what things we're trying to get from these designs. And then all in all, we decided that method one, that sandwich idea, was our best. So we wanted to pursue that further.
We then, once we had decided that we wanted a cold plate, looked into kind of some of the performance and how those are sized for manufacturers. Cold plates depend on the flow rate, the inlet temperature, and the heat load. The first two of which we can experimentally control, and the third is kind of what we're trying to find or control. The equations here, equation one calculates the outlet temperature to make sure that the temperature of the water coming out of the cold plate is cooler than the maximum temperature that we're trying to achieve on the top of that board. And then the second one defines the allowable thermal resistance of that cooled area. As you can see here, here's the example of a graph from a manufacturer kind of showing their different types of cold plates. This is the cold plate that we chose. As you can see, we have some of those flow rates that give us the different thermal resistivities.
Yeah, from there, we wanted to see how the heat would actually transfer to the system. So we made a thermal circuit. We knew that heat would be coming from our board and then it would transfer through conduction into our potting, then our aluminum into our cold plate, our copper piping, and then finally have some convection through that water, giving us the final temperature. Using this thermal circuit, we can get the total resistance of that heat transfer, which will allow us to find our overall heat transfer coefficient and also our heat flux through the system.
We also started making some representative FEA and CFD models. As you can kind of see here, this is the cold plate and the board that they're trying to model. You can see the hot spots at the top. These are using some placeholder values until we experimentally determine what those heat loads are from the overcurrent condition. But just to kind of get started on that process of creating those models and validating how kind of accurate they are.
In addition, we ran a CFD model to see how our heat would go through our system, see where the cold spots and the hot spots would be when we do mount this onto our tool.
And this is where we wanted to get kind of an initial setup going. This setup was nowhere near where a finalized setup would be, but it gave us a rough idea of how these cold plates work and kind of a rough idea of an experiment. So we set up a procedure. We consulted a MSOE faculty, Dr. Hayes, who had actually been setting up something very similar to a thermal fluids lab. And so we helped, and then we set up this experiment that included our cold plate set on top of a hot plate, which was turned up to the maximum temperature. And then we had water running from just a public faucet go in one end of the cold plate and out the other, while that outlet was monitored by a thermocouple hooked up to an Arduino board and then hooked up to the computer to get that graph that's shown up here. We ran a stability test just to make sure that everything was stable. But notice as we ran the experiment, there was a couple instabilities, including the water flow rate through the cold plate was a little inconsistent, as well as the heat plate shutting off once it reached its max value. So with those in mind, we decided that this was obviously room for improvement for a future experiment, but gave us a good idea of what to look for when running this.
From there, we needed to actually use this onto our tool. So our current consideration is to cut off our front of our saw so we can have some room to mount our cold plate and give us some more volume so we can incorporate our concept of the sandwich. In addition, it gives us more room to put our data acquisition devices such as some thermocouples, thermistors, get us some numbers from that.
Now, not only do we want to utilize this cold plate idea, we also wanted to evaluate if a custom solution would be viable as well. The motor head actually has 3 nicely mounted screws, and so we wanted to come up with an idea that utilized those placements to see if this puck idea could be utilized. A couple different iterations of this puck as shown, and the current standing solution or standing idea is this kind of version 5 of it. We wanted to make the actual frame of the puck made out of aluminum and the piping made out of copper. This is just due to the materials having really nice and high thermal conductivities. So then, like we've stated, that small surface area could be utilized and have the most amount of heat transfer that we could get.
So now we've talked about the cooling mechanism and the fixture. So this is the test procedure that we were going to be moving forward with. So we have the saw. First, we need to secure it using the test fixture and connect our data acquisition devices. So we'll be using thermocouples and an Arduino board for that application. We will also be pulling the trigger away from the saw so we have some distance between us and that. We also want to think about safety. So we're going to have a piece of plexiglass between us and the saw. And we're also going to be wearing our proper protective equipment during the test. Next, we would start that data acquisition, begin the water flow through the saw and through those cooling pieces. We would run that saw up to speed so it's at its operational speed and apply various levels of braking load using our test fixture. And we would stop once the saw stalls or overheats. Conveniently, the saw has a yellow light that tells us when it is overheating. Finally, we would analyze that data.
So now we're going to put that test procedure to use. Initially, our first testing was to answer the question, does our test fixture work as designed? And there's 3 big takeaways that we learned from this test. Yes, we were able to overload the saw as intended, but our braking pads were not able to withstand the force of the blade. And then another takeaway is that there was excessive vibration in our braking mechanism. So where does this lead us? This leads us into our future plans of where we're going with this project. For the design or for the test fixture, we'll be changing our brake pads to ceramic based material, which is commonly seen in cars. And then we also be supporting our brake mechanism so it vibrates less during load application.
And then for the thermal analysis side of things, when we ran that initial experiment, we saw a couple of those inconsistencies. So we want to be able to improve those. So when we finally get those final values from this testing rig, we're able to plug them right into our equations and run simulations as best as we can.
Do you have any way to measure brake load experimentally? And have you considered testing at different ambient temperatures?
So for the brake load, we can actually measure the current draw from the saw. That's our most accurate way of doing that.
And then I guess what specifically do you mean different?
I imagine the saw is being used at 100 degrees Fahrenheit and it's being used at 0 degrees Fahrenheit.
Yeah. So,
Account for that?
we also want to account for, so these saws are basically be used in any sort of applications. I mean, construction workers, I mean, they're working at any sort of heat all the time. And especially with the water source, I mean, they're probably just going to plug into the nearest faucet too. So there's a lot of variability there. We wanted to go with some initial, just like kind of standard temperatures, just to get like a temperature difference and understand if this water cooling works. But we definitely want to look into that variability of like if you're working in higher condition, like high temperature conditions, of how the water source and the saw get affected by that. And yeah, keep looking into that as well. Yeah.
I had a couple, but I'll do them kind of one at a time. You answered quite a few of my questions about the test fixture, but one I was thinking about is the blade itself. Is blade warpage something that is going to happen as the blade heats up under repeated cycling? And if so, how are you going to keep that from wrecking your fixture?
There's something we have not considered at this point.
Okay, I don't know. I know the blade is cooled. It's got slots in it, but I don't know if it will warp. It's just something I was thinking of.
Follow up on that is you have food pushing from one side. Is that gonna cause
That's another thing that we were considering. Currently the brake fixture has braking on both sides. The load application happens on one side. So ideally that pushes both brakes together so that it closes that. But we're still determining the validity of that.
starting?
No, because I'm just thinking of floating calipers on vehicles and making sure that doesn't bend or push the blade one way or the other. Another question is about the battery heat. When you did your heat test originally, it was under a no load condition and you said the battery looked great. How much do you expect the battery to heat up under load? And is that a major consideration?
Yeah, I think because we haven't run that test yet, we're unsure what that battery heat could look like. Again, a lot of the user complaints of battery overheating is a really general,
Yeah.
That's an easy spot for them to say like, oh, my battery was kind of hot, versus if the issue really is, okay, these specific components are getting way over there, supposed like the temperatures they're supposed to, that might be causing some of those issues. So we definitely want to track and see the battery overheating. But I think our goal was to try to cool those components and then see how that kind of affects that.
So part of this is sort of the root cause
Right.
investigation, right? What is actually happening that the customers are complaining about? Okay.
And that's kind of leads into like, we're in the middle of making that test fixture.
Yeah,
And
okay.
once we validate that test fixture works, then we can answer that question with confidence.
Yes, I can speak up to that. The user facing problem is, the tool side is overtemping, so we're not using the full capability of the battery. So when the packs are becoming like revved and they're better, the tool side is not taking advantage of that because the tool components are getting too hot.
Gotcha.
And then shutting the tool side down.
Gotcha. Okay, cool. Thank you.
Another question. You did a couple of things that you didn't mention in here. When you were running the test with the water cooler, what changes did you make? You remember?
Oh, yeah.
The lines that if you show the chart. The
Yes.
vibration that's taking place in there, what happens?
Yeah.
How
So
did you find?
in that experiment, let's make two sides. That thing's too far.
Yeah.
Almost. Yes. Okay. So yeah, just to kind of walk through it again. Yeah. So that initial temp stability, we made sure that everything was kind of steady, no huge inconsistencies there. But when it came to the inconsistencies that we did see, we noticed like just from like how the flow was coming out the outlet, it was kind of jagged. It wasn't very consistent. So we saw that there were issues there that could result in kind of variation in that heat transfer. And then that hot plate was kind of shutting off at that max temperature. Changes that we wanted to make to this and that we were trying to adjust for was we considered the idea of the tanks that we had used for a previous thermal fluids lab. And then after going one step further, we actually consulted Austin and got a hold of a Milwaukee tool tank that actually has a flow rate knob on it. So we could know exactly what the flow rate out of the tank would be. So we made that initial step right after the experiment was done. And then we're going to try to figure out an alternative to the hot plate. I mean, we don't exactly want to put this on like a kitchen stove, but if maybe that's the best option, we might pursue it. But it's definitely still things that we're considering in, I guess, the thermal application for this experiment.
You said the tool was those brake pads on one side, one brake pad on the other side, and you're supporting it by single, was it supported by single bolt or double bolt?
So it's got two bolts either side. So this bottom piece is actually a slot. And the reason why is because we want to be able to move the thing.
What about the brake pads? How is the brake pad is supported?
So this brake pad is fixed and then this brake pad is, this one is dynamic.
Normally brake pads have one bolt coming out and then you're basically tighten it. Is that what the same, so it was shifting like that? That's the reason for the vibration. Was it wobbling?
So the wobbling occurred at the base down here and then the back over here. Yeah.
Because the wear on the thing I saw it is also one-sided.
Yeah, and then another reason for that, I don't believe you mentioned it, but the cantilevered spring mechanism, it does drop a little bit because there's slop and holes. So that led to a bit of a higher friction at the top one right here. Yeah. Yes.
Do you know what testing Milwaukee tool did prior to releasing this stuff?
We didn't ask about this.
The Milwaukee guy.
We usually do like all bunch of different tests that we think they replicate. This would be closer to what a fixture test would be, or like a brake life, but in that case, we run like a disc. So it's like just a flat disc. And then once it's spinning, you just pinch the blade. And then that, like the saw will just go react. But that's to get like the clutch even. Otherwise, they just run it like cutting in concrete whole life.
I have another question. Maybe it's out of scope. It's about water cooling in general. As someone who has used a concrete saw quite extensively in my second job, water cooling's a pain in my ass. I don't like to hook it up. It makes a mess. It clogs. Is water cooling the only option available to you?
For the scope of our project, yes. I think Milwaukee Tool is looking at other alternatives to solve the issue. Putting some real engineers on that, but our scope was.
Okay, that answers my question.
Yeah, just the water.
I guess a big keyword is we're evaluating the feasibility of water
Okay.
cooling, so.
Thank you.
So you're pulling off of the same line that's being used for the blade and there's a dust reduction.
Yeah.
Are you using all of it? Are you using a fraction of it? How are you making that determination?
I think we're anticipating using all of it, having the most amount of flow go through a cooling plate. And that way we don't have to worry about kind of split flow or any sort of losses or anything like that. Because although the this is pretty like we have a lot of room to work with, we still want to kind of account for that so we're not like butchering the whole system that it was built on already.
So speaking of those losses, you led that right into, have you considered how adding more complexity in the device, particularly looking at channel size, et cetera, would rates and ultimately later cooling / device performance?
Yeah, we weren't given a specific like pressure that it's supposed to be at the end. And there weren't any specific OSHA regulations for what that had to be. So our kind of approach was to keep that diameter to the original as possible to reduce that pressure loss, which was kind of part of the reason why we were dissuaded from any like super micro channel applications or solutions. So our plan was to run our cooling plate as a test, and if we notice a significant pressure drop, to kind of address it there.
Yep. I'm not super familiar with these systems. You said it's used, the water's used for dust reduction. Kind of, does dust get in the water? Like, does it get?
Not,
Okay.
Not in the supply. Yeah, at the end of the saw, it's just like a mist of dust or mist to prevent the dust from being in the air and
so I guess,
affecting the health of the user.
yeah, long story short, like when you're using the saw, you're cutting it in concrete, there's a lot of dust that flies up in the air. Obviously, you don't want to inhale that and you don't want it get into the saw either. So the dust kind of fumes up and then it comes in contact with those the water dusts up and comes in contact with the dust. And then it kind of like helps mitigate all those fumes and vapors in the air.
Okay, if there's any questions, we got 1 minute, otherwise we need to move on.
Yes, I have one. You guys showed up that you're showed that you're cutting the housing to add the cooling plate. I guess, why are you cutting the housing? Does the cooling plate interfere with it? And if you are cutting it, did you plan on how you're gonna seal it back to minimize any external airflow that's gonna cool off the PCBA and give you positive support, negative, positive?
Yeah, so currently we're planning on cutting it because there's just not enough room to implement our sandwich design on there right now. It also gives us more room to work with to like get that data for the temperatures and everything. We haven't exactly talked about how we're gonna seal it right now, but that is something we consider.
Yeah, you guys can print use plastic pieces, some sort of housing, minimize.
Yeah. The beauty of water cooling is that we don't really need much airflow to help with that process. So we can make it a pretty close system.
All right, thank you, guys.
I think you guys saw. We did like a high school musical, like thank you.